Welcome to session 8 on the topic TRIAC, which is part of Unit 1 on power semiconductors under the course Power Electronics for 5th semester diploma in Electrical and Electronics Engineering. In this today's session, one will be able to draw the layer structure and explain the operation of triac and draw its VI characteristics and explain the four different modes of turn on of triac and in the end state the preferred mode of turn on of triac. Triac is a three-terminal bidirectional switching thyristor. It can conduct in both directions when it is triggered into conduction state. The triac is equivalent to two SCRs connected in anti-parallel with a common gate. The figures shown here are figure A shows physical construction of the triac. Figure B shows the two thyristor analogy and figure C is the circuit symbol of the triac. The structure of a triac is seen in this figure, shows the structure and its symbol. It consists of three terminals, namely MT1, the main terminal 1, MT2, main terminal 2, and gate G. The gate terminal G is near the MT1 terminal. The gate G is connected to the semiconductor layers N3 and P2. MT1 is connected to the semiconductor layers N2 and P2 and the terminal MT2 is connected to N4 and P1. Operation of triac. When no signal is applied to the gate, the triac is in cutoff state. However, the triac turns on when the applied voltage between the terminals MT1 and MT2 becomes equal to breakover voltage of the triac. When a small positive or negative voltage is applied to gate with respect to MT1, the triac turns on at a voltage less than breakover voltage. If the applied voltage at MT1 is positive with respect to MT2, the current flows from MT1 to MT2. If applied voltage at MT2 is positive with respect to MT1, the current flows from MT2 to MT1. Once turned on, the triac latches into conduction and the gate loses all control. And if you want to turn off the triac, then the current should be brought below the holding value. VI characteristics of triac. The figure shows the VI characteristics of the triac. The characteristics of the triac is similar to that of an SCR, both in blocking and conducting states. An SCR can conduct in only one direction, whereas triac can conduct in both the directions. The triac can be operated in four triggering modes. Mode 1, Mode 2, Mode 3 and mode 4. Mode 1 operation. MT2 is positive and gate current is also positive. When MT2 and gate current are positive with respect to MT1, the gate current flows through P2N2 junction as shown in the figure. The junction P1N1 and P2N2 are forward biased, but junction N1P2 is reverse biased. When sufficient number of charge carriers are injected in P2 layer by the gate current, the junction N1P2 breaks down and the triac starts conducting through the layers P1, N1, P2, N2. Triac in this mode operates in the first quadrant of the VI characteristics. The device in this mode is more sensitive, and this mode of triggering is recommended for achieving the desired conduction in first quadrant. Mode 2 operation. MT2 is positive and gate current is negative. When MT2 is positive and gate G is negative with respect to MT1, the gate current flows through P2N3 junction as shown in figure B. The junction P1N1 and P2N3 are forward biased, but junction N1P2 is reverse biased. Hence, the triac initially starts conducting through P1N1, P2N3 layers. As a result, the potential of layer between P2 and 3 rises towards the potential of MT2. Thus, a potential gradient exists across the layer P2 with left hand region at a higher potential than the right hand region. This results in a current flow in P2 layer from left to right, forward biasing the P2N2 junction. Now, the right hand portion P1N1 P2N2 starts conducting. The device operates in first quadrant. When compared to mode 1, triac with MT2 positive and negative gate current is less sensitive and therefore requires higher gate current for triggering. In mode 3 operation, when MT2 is negative and gate is positive with respect to MT1, junction P2N2 is forward biased and junction P1N1 is reverse biased. N2 layer injects electrons into P2 layer as shown by arrows in figure C. This causes an increase in current flow through junction P2N1, resulting in breakdown of reverse biased junction N1P1. Now, the device conducts through layers P2, N1, P1, N4, and the current starts increasing, which is limited by an external load. The device operates in third quadrant in this mode. Triac in this mode is less sensitive and requires higher gate current for triggering. Mode 4 operation, where MT2 is negative and gate current is also negative. In this mode, both MT2 and gate G are negative with respect to MT1. The gate current flows through P2 N3 junction as shown in figure D. Layer N3 injects electrons as shown by arrows into P2 layer. This results in increase in current flow across P1 N1 and the device will turn on due to increased current in layer N1. The current flows through layers P2 N1, P1 N4. Track is more sensitive in this mode compared to turning on with positive gate current of mode 3.
The figure shows the VI characteristics of track. The voltage V is applied across the terminals MT2 and MT1 and is shown along the x-axis. The current flow I through the track is shown along y-axis. The figure also shows the operation of triac in various modes in different quadrants. Basically, the triac operates in two quadrants, that is, quadrant 1 and quadrant 3. The triac operates in mode 1 and mode 2 in quadrant 1 and in mode 2 and mode 3 in quadrant 3. In mode 1 operation, the track with MT2 positive and positive gate current is more sensitive. Hence, it is the recommended method of triggering. In mode 2 operation, the track with MT2 positive and negative gate current is less sensitive and requires higher gate current for triggering. Hence, this is not desirable. In mode 3 operation, the triac with MT2 negative and positive gate current is less sensitive and requires higher gate current for triggering. Hence, this mode is not desirable. In mode 4 operation, the triac with MT2 negative and negative gate current is more sensitive. Hence, it is the recommended method of triggering. Therefore, from the characteristics, it is clear that in quadrant 1, track is operated in mode 1 and in quadrant 3, the track is operated in mode 4.
The most preferred mode of turn on of a track sensitivity is greatest in the first quadrant when turned on with positive gate current and also in third quadrant when turned on with negative gate current. When MT2 is positive with respect to MT1, it is recommended to turn on the track by a positive gate current. When MT2 is negative with respect to MT1, it is recommended to turn on the track by negative gate current. Therefore, mode 1 and mode 4, that is quadrant 1 and quadrant 3, are the preferred modes of operation of a triac. Applications of track. Track have a wide application. They are applied as lamp dimmers for controlling the dimming of lamps. heat control to vary the heat, speed control of small single phase motors, example ceiling fan or table fan, as a AC static switch, and also as a time delay relay. So the summary of today's session is a track is a three-terminal bidirectional switching thyristor. VI characteristics of track is similar to that of an SCR in both blocking and conducting states. The track operates in four triggering modes. The preferred mode of track, that is turn on of the track, or mode 1, where MT2 is positive and gate current is positive. Mode 4, MT2 is negative and gate current is negative. Mode 1 operates in quadrant 1 and mode 4 operates in quadrant 3. Track is used as a AC static switch, time delay relay for speed control, heat control, and lamp dimmers, etc. Dear students, let us see how much you have learned or understood about track in this session. So just answer these multiple choice questions. Question 1. A track has three terminals. 1. Drain, source, gate. 2. Two main and a gate. 3. Cathode, anode, gate. 4. None of the above. What is the answer? The answer is 2 main and a gate. Question number 2. A track is equivalent to two SCRs in parallel, in series, in inverse parallel, series, opposition. So the answer is third one, in inverse parallel. Question number 3. A track can pass a portion of dash both positive and negative, neither positive nor negative, only positive, half cycle through the load. The answer is first one, both positive and negative half cycle through the load. Question number 4. VI characteristics for a track in the first and third quadrants are essentially identical to those of 1. Transistor, 2. SCR, 3. UJT, 4. Diode. The answer is 2. SCR in its first quadrant. Question number 5. A track is a dash switch, bidirectional, unidirectional, mechanical, or electrical. So the answer is first one, track is a bidirectional switch. Question number 6. A track has dash semiconductor layers. So how many semiconductor layers are there in a track? So there are 4 semiconductor layers.
Question number 7. A track is a three-terminal bidirectional switch, two-terminal switch, three-terminal unilateral switch, two-terminal bilateral switch. The answer is 1. Three-terminal bidirectional switch. Question number 8. Which of the following is not a characteristic of the track? Gate current, holding current, peak point voltage, latching current. The answer is 3, peak point voltage. Question number 9. A track can be triggered only by the positive half cycle of the supply, only by the negative half cycle of the supply, both by the positive as well as the negative half cycles of the supply, by none of the above. The answer is 3, both by the positive as well as the negative half cycles of the supply. Question number 10. A triac can be triggered into conduction by only positive voltage at either of its main terminals, 2. Either positive or negative voltage at its gate, either positive or negative voltage at either of its main terminal. Both 2 and 3. The answer is 4, both 2 and 3.